Okay, you're welcome to today's session. We are going to continue from random variables 1, where we left off last time. So, if you remember from random variables 1, we're talking mainly about discrete distributions. So, that's why we're talking about Poisson distributions, hypergeometric distributions, and yes, so those are the major things, and binomial distributions actually. So, those are the major things that fall under random variables 1. In random variables 2, we are going to be talking mainly about continuous distributions. And then as we define the random variable, it's a function defined over a sample space. So it is not necessarily a number, right? It's not really a number. So it's, yeah. So the major probability distributions we'll consider in continuous distributions would be probability density functions, that's PDF, and then CDF, right? Okay. Okay. So the next thing here is to note some of the rules or some of the things to take note of when you are dealing with probability distribution functions. So here, if you define any probability within any two ranges, right, then you can um, you can imply that as the integral of the function of x dx. Now this f of x dx is actually like um, is the value, right? Is the value of x at a particular point. So let's say we are considering at x equals 1 here, then you can have your f of x being here, another f of x, f of x. So as the values change, then all of that changes too. Now why are we using the integral? Because we are summing up everything. So that means we are summing up everything. And when we do that, we get something like this. So there's this thing they say that the continuous distribution function is actually smoothened. Sorry for my handwriting. Is the smoothened discrete distributions, right? So when you smoothen this, you get this. Okay. Now, just a few things to note that at any point, your f of x will always be greater than 0, and then when you add up everything, you should be getting 1, just like in probabilities. Okay. And then the probability at a single point just gives you 0. I'll explain this one when we move on. Okay. But then for now, let's just move into trying to understand some of the examples, and then so let's just start the first one, the density function. So they will give you for instance, let's say they will give you the f of x. So let's just use the example about some battery half-life. So they can give you, say, f of x is negative 0.16x plus 0. Negative 0.16, sorry. And then so this one is between 1 year and then 3.5 years, but okay. And then we have 0.96 minus 0.16x for 0.5 less than or equal to x less than or equal to 6. So these are in years, okay. And then 0 otherwise, right? Okay, so let me just explain this question briefly before we move on. Okay, so it looks like you've manufactured a battery, right? And then you're trying to evaluate the battery's performance over years. So approximately the battery is supposed to last like 6 years, but within that 6 years, it's not going to perform so well, like continuously. So the performance from 1 to the 3.5 years will behave like this, right? And then from 3.5 years to 6 years, it will behave like that. And then for the rest of its lifespan, it will simply spoil. So, what if they want you to find the probability that the battery lives for more than 3 years? For more than 3 years. So that means that part of that 3 years enters into this first function here, right? And then part of the rest. So let me suggest that the rest of it remains here. So particularly this question, there are two ways to solve it. You can either find the probability less than 3 years and subtract it from 1. So the probability that it survives less than 3 years and subtract it from 1. Or you can just find the probability here, right, and add it to the probability here. Either ways, you still get the same thing. So let's start with the first one. So that means that we'll need to find from 3 to infinity of f of x dx. Okay, okay, let me write this well. Okay, now if we want to find this, then that means first of all we have to do from 3 to 3.5 of f of x dx plus integral from 3.5 to 6 or to infinity of f of x dx, because from, okay, so let's just do it for courtesy sake. Okay, did I just say courtesy? Okay, okay, mathematical courtesy or something. So from here, right, from this point we can say that 3 to 3.5. Now what is our f of x? For that range we have negative 0.16 plus 0.16x dx plus from say 3.5 years to 6 years, that gives us 0.96 minus 0.16x, right, dx plus 0. I hope you agree with me. Okay, now let's say even if you try to visualize this graph, right, you find that it will look something like this. So it will look something like this, um, right, and then it will come down by the same, something like this, right, and then from here onwards it just becomes 0. So it looks something like this. But then anyway, so let's just, so in piecewise form you can describe this with the positive gradient side and then this with the negative gradient side. When it gets to 6, it starts zeroing all around, and then from here it starts. Okay, so how do we solve this? There are many ways to solve this. You can decide to put this into your calculator and then just get it in the case of OBJ, or you can decide to solve it manually. Either way you get the answer. So I'm assuming that everyone knows how to enter this into a calculator, but if you don't, just check the integral sign. Let me see if I can get you an example. Okay, so you just have to do this, um, negative 0.16 plus 0.16 x, okay, and then from 3 to 3.5. Then you can solve this, put down your answer. So this will be 0.18. Then you solve the next one, put down your answer. If you actually do it, you get 0.5. So when you add them, you get your 0.68. So this is the probability that it will survive over 3 years, right? Now, so that means that there's a high probability that it will survive over 3 years. Now, the other way I said you could solve this was probably working for, so you could find integral from 1 to 3, right, of negative 0.16 plus 0.16x dx. So you can just do 1 minus this. Okay, so let's try that. So I just have to change, okay, so I just have to change this, okay, so you get 0.32, right, and then you just take 1 minus this gives you 0.68. So either way you still arrive at the same answer. Okay, so there is some properties you have to take note of, right? So when you are considering a continuous distribution, so it can take any form, like this or that, or can take a form like this. Now, anyhow it takes, right? There are some things you have to take note. So let's say I have here to my point A, point B, right? Now, at each of these points, it doesn't matter whether you take the limits from that point or right after it or right before it, you still get the same thing. Let me explain. So you have probability of A, right, less than X less than B. Now this one is the same thing as taking this or this and leaving this as this. Anyway, you still get the same thing, right? Or you take this and leave out this. So what I'm just trying to say is that this, right, x less than b equals probability of a less than or equal to x less than b, probability of a. I don't know I'll ask you about this, but it's just good. So all of these they will give you the same thing, which essentially means that the that area under it, right, is simply this, right? Yes. So that's just it for that part. There's another example here. Let's just try this one then move on with the rest of the discussion. Okay. Okay. So let's take a function, right? So we are going to take a function of x that is described as 20 e power negative 20 x minus 1 12.5. That's for x greater than or equal to 12.5. Oh, sorry, 12.5. Okay. Okay. So this function describes a manufacturing process where they have a metal sheet, right? And then they'll always try to say make holes through it, maybe for whatever reason. But then if you make a hole that is greater than, say, equal to or greater than 12.5 millimeters, right, the the machine or whatever they use tends to make it larger, right? So let's say if you are going for 13 to make it larger, so now you are trying to calculate the probability, right, that um, the target now, so this is the target, but then you are trying to make another one of, say, 12.6 millimeters. This is the question in the slide, right? So what proportion of the part is scrapped, sorry. Okay, so from this we know that this function is defined for x greater than or equal to 12.5, and this is greater than 12.5. So that tells you that the probability that your x will be greater than 12.60 would directly be from 12.60 to wherever it can reach of the function. So I just say f of x dx. Alright, so this can be equal to your integral from 12.60 to infinity of 20e power negative 20 x minus 12.5, right? And then you say your dx. As usual, you can solve this with your calculator, but then if it's theory, then you need to work out. So that means you have to revise um, how to do your integrations, right? So how do you? Okay, so let's take it again. So we want to solve integral from 12.6 to infinity of, say, 20 e power negative 20 x minus 12.5 all the x. Okay, now you can use your substitution method for this. You can also go with the direct method. Actually, you can go directly, but then substitution will be easier. So you can say let u equals okay, let's just pick everything. So let's say negative 20 x minus, right, then in this case that makes um, okay, right, negative, right. So in this case you can have your negative x equals negative 1 on 20 du. Okay, so with this set you can decide to put it back, so you can have 20 e power u and our dx, which is dot 1 on 20 negative 1 on 20 du. So we can now integrate, but then you have to take your time. You can't use 12.6 again because you used so let's just keep this one. Let's leave this one up, and then this one will cancel out, so you end up having negative e power u du. Good. Now at u equals 12.6. Okay, then that means your x at x equals 12.6, then your u will be equal to what? So if you put 12.6 here, what happens? Yeah, you get 0.1, so that'll be minus 2. Right, so that means and then if you put x equals infinity, no, you can't say equals infinity. So when you put x approaches infinity, then basically that same thing also approach infinity. Okay, okay, to approach negative infinity, which is still the same thing. Okay, okay, so that would mean that our final this one would be from, okay, so we'll have from minus 2 to minus infinity. Okay, I'm contemplating whether the arrangement is right, but then yes, basically that's the main idea. And then we have our negative e power u du. Good. So that means we are set now. So if you solve this, what do you get? You practically get the same thing, but you can bring the negative out. So that means you end up having your negative um, e power, say u, right, from negative 2 to minus infinity. Okay. Okay, and then this would give you, sorry. So from here, this would give you your negative. Let me draw a line here. So this will give you a negative a power negative. It's not allowed though, but then let's say u, where u approaches infinity. Okay, and then minus e power negative 2. Now this one, e power negative u as u approaches infinity, is basically 0. You can try to experiment it here. Where is it? Okay, so let's say negative 99999. Right? Yeah, approximately get 0. And then, so that means you only be left with e power negative 2, because the two negatives will cancel out. And then when you calculate e power negative 2, um, e power negative 2, then you end up getting 0.135. Okay, yes, so basically that's it. So in cases where it's theory and you have to go through the long process, you'd have to go through all of these calculations. Maybe there are shorter methods, but then this is just fine. It does the work too. Okay, so let's move on to the next thing on the list. Okay, so just a small clarification here. In the whole of these lectures, he uses two major things, right? So at some points you see probability distribution, you see probability density. Yeah. So basically, they try to basically show the same thing, but there are slight differences. So when we talk about so the slight difference is that the probability distribution function is actually like a general concept for all the possible distributions, right? So it can either apply to discrete or continuous, but then probability density function is strictly for continuous, right? So this one is strictly for continuous. So that's just what I want you to note. Okay. Okay, so we've done this slide example, we've calculated this, and then we've also tried for the example about a metal sheet. Now let's move on to the next thing. Okay, so the next thing is cumulative distribution function. But to make it easier, I would just stop here, right, and then record this in another video for people who just want to watch this one. Okay, thank you for watching, and I'll see you in the future.